University of Texas Quest Physics Energy Transformation Problem Set. Call this the block jump ramp. All right, we're given a mass, a known mass in grams. Make sure you convert it to kilograms. What it does is it slides down here. So it starts at rest. So its potential energy is this mgh. Kinetic energy is 0. All right, so what it does is it loses potential, gains kinetic until it gets to this point right here, just a simple energy transformation. Now this part's a little bit tricky. Here, this has friction in it. So I'm going to have a force of friction acting this way over this displacement. So what I have here is I have some energy removed by the negative work done by friction. Still has some velocity left over, so it flies off this ramp at some velocity, and then I have a half parabola projectile motion until I finally impact the ground. Now all these variables that I have a check mark by, those are the things that are given in the problem. All right, there's a number of ways to work this problem. The way that makes at least the most sense to me is we're actually going to work backwards. And the reason I'm going to do that is, one of the problems says, well, what is this velocity that flies off the ramp? Now, I've marked these points 1, 2, 3, and 4. But believe it or not, I'm actually going to start with point number 3 because I want to know this velocity. If I can fix this velocity and I know this height, then I can fix my total energy right here at point 3. And that's kind of the hinge pin of this problem. All right, so how am I going to find this velocity at 3? Well, I'm going to work kinematics. And I am going to use my favorite equation for finding time in a half parabola. And I'm going to use that time then to find this velocity at point 3. That's the velocity at which it flies off the ramp. And then once I have that velocity, now what I can do is I can fix my energy at point 3. My total energy at point 3 is going to be a summation of my kinetic energy at point 3 plus my potential energy. My 1/2 mv squared. And where did I get that from? I got that from my kinematic stuff. So I know this guy. All right, and then my mg8, that's my potential energy at point 3, that dy. That's my distance above my reference for my potential energy. I called here, this ground level, I called that 0 potential energy. All right, so that means right here I have both kinetic and potential. All right, so I get my total energy at 3. All right, now I go from point 2 to point 3, and there's work done by friction. So I know the work done by friction is going to be negative. So I'm going, basically E final minus E initial. So I'm going to get to point 3 from point 2. I'm just setting it up this way so all my plus and minus signs work out. All right, just a little bit of algebra here, and I find that my total energy at 2, right here before my sticky spot, is the total energy here plus the work done here. I've got a higher energy here than I do here, which should make sense. All right, so this guy we have fixed. All right, we've already computed him on this line right here. All right, so now I need to get this work done by friction and add it to it. Well, I know that that is going to be mu force normal, which in a horizontal situation is going to be equivalent to the weight. And then this displacement along this frictional path is given. So what I can do is I get my total energy at point 2. All right, now my total energy at point 2, I've got that fixed by energy transformation, needs to be equal to my total energy at point 1. And I know at point 1 I started from rest, so kinetic energy is equal to 0. So that means my total energy at point 1 is all wrapped up into potential energy. So I can just simply solve for H. Right? And then that gives you all the information that you need for this problem. Okay, one last part of this problem that it asks for is it asks for the speed here at point 4. And the way that we're going to solve that is I can go, well, my energy total at point 3 has to be equal to my energy total at point 4. And remember, this we have completely fixed. I've got a number for that. So that means that is going to have to equal to the kinetic energy at point 4 plus the potential energy at point 4. But my potential energy at point 4, I'm down at what I call my 0 reference point for potential energy. So that's 0. So that is just going to be equal to 1/2 mv4 squared. Okay, so that actually turns out to be very, very simple. Now, if I was to do this with kinematics, that's a two-dimensional velocity. I had to find v phi on the y, add them together Pythagorean, blah, 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 blah. That would work, but here I can just get it in one step. And that should answer all the parts of this problem for you.